These are examples of manifold. Example of manifolds. The first example is very easy. The Euclidean space Rm, and this is the most trivial example. Manifolds. Please note that we are only considering spaces with real numbers, or so to say, we are only dealing with real manifolds for now. In m-dimensional Euclidean space, you can actually use a single chart cover to cover the whole space, and you can choose the homomorphisms to be the identity map, because this is just a map from, if you take m equals to 2, let's say xy, then any point P over here can be assigned 2 coordinates. That means the value of x and y in such a way that this is just x and y of P. And you can choose any chart at all. It can be very big, it can be small. If you take small ones, you have to use multiple, but you can even take a very big chart that will cover all the points. So this is a more of a special case that you are seeing. The example 2 is that the circle S1 is a manifold. How can we see that? Well, let's first draw a circle. What we can do is that we can choose to have 2 charts that will cover the entire circle. That means all the points on the perimeter. And let's define some phi inverse 1 map that takes values from this open interval and maps to S1. If I do that, then what is happening? And you can easily see that to cover the circle, this phi inverse 1 will actually need to take some theta parameter, and for the circle this is just the angle, such that this is cosine theta and this is sine theta. So what is happening is that this phi inverse 1 is taking points from this interval, this open interval, and mapping it onto the circle here. And in that way, since this is an open interval 0 and 2 pi, you can see that the point over here is not getting mapped. So we need to have another chart. Okay, this is acting as the chart. So we need to have another chart that will cover this point and the other points. So now we take another chart defined as, let's say, phi 2 inverse 1. Again, it takes some theta and maps it to, let's say, cosine theta, sine theta. However, now theta ranges from, sorry, not theta, this value of phi 2 inverse 1 takes elements from this minus pi to pi. So let's say this is minus pi, this is pi, and now you can see that this 0 falls in between over here, right? and this map will cover this point that we initially failed to cover with this chart 0 to 2 pi, but now this point is covered. However, we will see that now this point over here is not covered. So essentially, by taking two charts, let's say you take their union, if you take their union and you take these two maps, you are essentially covering all the points on the circle. And also note the fact that this phi inverse 1 and phi 2 inverse 1 are invertible as well. So basically phi 1 inverse, phi 2 inverse are continuous. These are also your homeomorphisms, and you can also verify that the transition functions 1 2 denoted by phi 1 composed with phi 2 inverse 1 and psi 2 1 as phi 2 phi inverse 1 are also smooth. So it satisfies all the criteria of being a manifold, and hence we call it a manifold. So the circle itself is a manifold. Okay. Note that by saying smooth, what we mean is that these things are infinitely differentiable. What we could do is that we could restrict ourselves where we have the kth order, let's say the kth order differentiability. However, that doesn't bring us an interesting result. And by saying infinitely differentiable or smooth, what we mean is that if you have a function, let's say, and if you can take derivatives of its derivatives, that means all the derivatives that you produce, let's say you take the first derivative, but now you can differentiate it again, you get the second derivative, you can differentiate it again to get the third derivative, and so on. So that's what we mean by smooth. Okay. Similarly, another example of a manifold is Sn, which means the n-dimensional sphere. And this Sn is just given by this equation. Oh, sorry. Instead of 0, let's use 1. I equals to 1 to n. So this is just x1 squared, x2 squared, x of n squared. Let's say it's a unit n-dimensional sphere, so you can just write it as 1. This is also a manifold, and it can be realized in any R n plus 1 dimensional space. For example, in 3D space, you can have a sphere which is the 2 sphere, S2. The surface of this the sphere is denoted by S2 because the surface is a 2-dimensional subspace of the 3-dimensional space. Okay, now that we are done with examples and definitions of a manifold, we would like to move on and discuss some tools that will help us to develop the calculus on manifolds. And we can do that, and we will do that, but before we start that, let me write a brief comment.